there are some cases where a matrix will not reveal a unique solution. And let's take a look at a couple of those cases. So in case 1, the system is we have x plus y equals 4 for the first equation and 2x plus y equals 8 for the second equation. So we write down our matrix, we row reduce, and we obtain the following matrix, right? So the first row says 1 times x plus 1 times y equals 4. So x plus y equals 4. Well, that's consistent with this first equation here, right? The second row says 0 times x plus 0 times y equals 0. So it says 0 is equal to 0. This is a true statement, right? It is consistent, but it is not revealing anything new about the system and is not revealing a unique solution. So in fact, we see that this second equation is simply an integer multiple of the first. That is, if we multiply the first equation times 2, we will obtain this second equation. So 2 times x is 2x, and 2 times y is 2y, and 2 times 4 is 8. So we see that this second equation is not revealing any new information, right? And in fact, there are an infinite number of solutions to this system because if we graph both of these, right, we get negative x plus 4 for both lines, right? So they simply graph the same line, and there are an infinite number of points on a line, so there's an infinite number of solutions. And we could think about it in the following way quite easily. In terms of x comma y, we could think of just a couple of solutions off the top of our head. Well, 2 plus 2 equals 4, right? So 2 comma 2 is the solution. We could have 3 comma 1, 1 comma 3, negative 5. Well, let's try. Well, negative 5 would work. Negative 5 and 9, right? Negative 5 plus 9 is 4. And we could have, negative 1 comma 5. We could have 5 comma negative 1, on and on and on, right? And all of those are valid solutions, and we can think of an infinite number of combinations that would satisfy that system of equations, right? Okay, the second, and these ideas, although we're doing a simple case in 2 dimensions, right, these ideas could extend easily to an infinite number of dimensions, to a system of any size. So, let's consider the second case. In case 2, we have x plus y is equal to 4, and we have x plus y is equal to 2, right? Well, if we write down our matrix, we row reduce, and we obtain the following matrix, which could occur on an exam or otherwise, and we want to be aware of what's going on whenever we get a matrix like this coming out, right? The first equation says the first row, rather, says 1 times x plus 1 times y equals 0. The second row says 0 times x plus 0 times y equals 1. So the second row says 0 is equal to 1. This is not a true statement, right? And what it's telling us, what it's indicating to us, is that this system of equations, right, is inconsistent. That there is no solution to this system of equations that satisfies both. There's no solution that will satisfy both these equations. And in fact, if you plot this one, right, if you plot these equations, right, you will get 2 lines that are parallel to one another. They never cross, and there is never a solution that will satisfy both. And you can see that easily by looking at them. If x plus y is equal to 4, x plus y cannot also be equal to 2, okay? So we want to be aware of this when this might come up. And the third situation is the situation that we all know and love. It's a system where, in fact, it does row reduce to a unique solution. So we have x plus y is equal to 4, and x minus y is equal to 0, right? So then we write down our matrix, we row reduce, and we get 1 times x plus 0 times y equals 2, and then 0 times x plus 1 times y equals 2. So x equals 2 and y equals 2, and we see easily that that does in fact satisfy these. 2 plus 2 is equal to 4, and 2 minus 2 is equal to 0. So these equations are both satisfied by that solution. If we plot the lines, y equals x for the second equation, this is the line y equals x. And then the second line, or the line corresponding to this equation, is y equals minus x plus 4. We'll see that they'll cross, right? And they'll cross at the point 2, 2, right? Or in terms of x, y, I guess it would be 2, 2, right? Because we usually write x comma y, not y comma x. So this is the situation that we all know and love. This is what will usually turn up in our equations that we are, if we're writing down consistent physical equations according to the laws of physics, usually we will end up with unique solutions if we have written down a number of equations that is equal to the number of unknowns. We should be able to solve that system for a unique solution, right? However, these two situations will show up. If this situation shows up, it doesn't mean that we've done anything wrong, right? It just says that we've written down an equation that doesn't give us any new information. For instance, the junction rule, where you go into one side of a parallel circuit, you write the junction rule going in, and you write the same junction rule coming out. I1 is equal to I2 plus I3, and then on the other side you write I2 plus I3 is equal to I1, and you haven't given anything new you haven't contributed any new information to that system of equations, right? So this could show up where we have not made a mistake, but we just have not written down equations that are revealing unique information. And in this situation, it's likely that we've made a mistake if this situation shows up. So we want to be aware of these situations so that we can respond appropriately on a test or otherwise, right? And these are the matrix caveats, as it were. So I'm going to step aside and give you a clear screenshot. I was going to say try them for yourself, but at least take a look at them and understand them so you know what to do whenever this shows up. Because this is a two-dimensional example, obviously a very simple example, but this can extend to any number of dimensions, right? You could have 50 equations with 50 unknowns, and one of them, just one of the equations, is not giving you unique information, and then you'll get 0 equals 0 on the last row, right? And there will be an infinite number of solutions. So it is important to understand these exceptions. So I am going to step aside and give you a clear screenshot. Take a look at it.